Here's the thing on efficiency. So I did a measurement with a 75 kVA transformer. I put a really bad harmonic source on, which was a bunch of computer power supplies. And I distorted the voltage and I distorted the current. And I looked at, with a resistive load compared to that 100% harmonic load, what's the efficiency difference on a standard transformer? And across the range here of loading is about a 1% change. So if somebody sells you a magic box that they say, this, put this in and it'll get rid of all your harmonics and you're going to save about 30% of your power, is that true? No. Now if they say it saves about 30% of your losses, is that true? Pretty close to true, right? Because what, your losses here were 2.5% and now they're like 1.5%. So people can play games with words, but the ultimate idea here is that you're only saving 1% of your losses. Okay, if you filter it out 100%. But anyway, that kind of stuff is really important to realize. So harmonics, just like power factor correction, do save you a little bit in losses, but it's not 20 or 30%, it's 1 or 2 or 3%. Okay. Kind of rule of thumb of harmonics, if you have less than 10% of your load for your transformer, it's probably not an issue. 10 to 20%, you probably want to do an analysis, and above 20%, more than likely you want to do a study. And simulating this stuff it's not always easy. It's it's dependent on what the customer might believe the load is, what you might believe the load is. It's not always evident. So you have to kind of figure that out. The other thing that I will tell you though is if you have a whole bunch of drives down here and you're trying to figure out your 519 compliance, make sure you add in a linear load there. Why? Because you are going to have linear load. What's a typical linear load? A whole bunch of motors that are running across the line. That in combination with the harmonic load is going to make your current distortion go down in terms of percentage, and it's going to be more realistic of what you have. If you completely ignore your linear load, your current distortion is going to artificially be higher. Your voltage distortion, by the way, doesn't matter. It's only going to be affected by this. But your current distortion will definitely be different. That's kind of the breaking point of, okay, now we know we have some harmonics in the system. What can we do about harmonics? And what can we do to get rid of them? Okay? There's a whole lot of different solutions here, including filters. Low distortion loads for lighting and things like that, harmonic mitigating transformers, broadband filters, 12 pulse rectifiers, a lot of different things, active filters, or maybe you just oversize your generator. What happens if I really need a 1,000 kilowatt generator, but I put a 2,000 kilowatt generator? What have I effectively done? Reduce the impedance. So over here where my impedance was 18%, now it's on the nominal basis compared to what it should be, it's 9%. So now my impedance difference isn't as big of a deal. Yeah. But it cost me a lot more money to do it, right? So here's some of the typical solutions for drives, and we'll talk a little bit about each one of these. So here's the thing, Adrian already showed you a little bit about this, but this is actually out of the IEEE standard, and it basically shows a 6-pulse drive with very little impedance. Really what they're saying is you need a little bit of impedance to make the thing work and not blow up. But a capacitor on the DC bus of a drive, capacitors don't like to instantaneously change voltage. So the capacitor is going to draw a current that's very, very steep. It can change current as quickly as it wants, right? Except for the fact that you have an inductor in front of it. If you have a choke, an inductor, an AC or DC bus reactor, it's going to slow that current down. And so when you have those two elements kind of competing with each other, current doesn't like to change instantly through an inductor, voltage doesn't like to change instantly through a capacitor, you kind of have to balance that out. And so what you end up with is, with a reactor in front of a drive, you reduce the harmonic current substantially. And as I mentioned, the harmonic currents go down as you go up in frequency. So the fifth harmonic here is significantly less over here than this one. Also, if you look at the RMS current, 148 amps, 117 amps, I did actually reduce my RMS current through the system as well. Here's an example of using an isolation transformer in front of a drive compared to just having a small reactor inside the drive. Okay? So you see the wave shape here and the wave shape there. This looks more linear, more 60 hertz like, and less harmonic current. So the fifth here is 9.92 amps, Fifth here is 15.97 amps, okay? So you're reducing the harmonic current. Why does that transformer work? It works just like the line reactor. It has an impedance of a typical transformer, 5, 6, 7%. So it works just like the impedance of a reactor. Now if I take a 100 horsepower drive and I put a 2500 kVA transformer in front of it, even though it has 5.75% impedance, it's not going to do much for my reactance of the drive. It has to be more matched to the size of the drive. So 100 horsepower drive, if I have a 112 kVA transformer, that's going to be pretty close, and I'm going to get that 5% effective impedance on it. A lot of people use drive isolation transformers, and that's the benefit of it initially. Plus you can do phase shifting with it as well. Here's the other graph that Adrian showed, and what this shows is you kind of get diminishing returns. So as you go up in impedance, the next level here, 8%, 10%, you're not going to get as much out of that reactor as you go up with in impedance. So 3 to 5% is perfectly fine and going to work well in the power system. How does a harmonic filter work? A harmonic filter, current wants to flow to the path of what? Least impedance, least resistance, right? So if this filter's not here, and these drives produce 12 amps each of fifth harmonic current, all that fifth harmonic current is going up through my transformer or up through my generator, okay? What I'm trying to do with a filter is convince the current to go somewhere else, which is some of it's going to go here, some of it's going to go to the generator if that's online, and some of it's going to go back there. By taking the current and not pushing it through that impedance, what have I effectively done? I've stopped the voltage distortion from happening. Do I have to make it a perfect filter? Does all the current have to go here? No. It just has to be less than what it would be, in a normal situation. Now typically we tune these filters to something just below the fifth harmonic, because the fifth harmonic is the predominant harmonic. And this is a multi-stage filter, 25, 50, 75, 100, 125. And you can see with a small filter, the impedance, okay, is higher than with a big filter. So the bigger the filter, typically the lower the impedance. What's the downside of putting a really big capacitive filter, which is basically a capacitor and reactor? What's the downside of putting this huge monster filter on there? If I put too much capacitance on, I'm going to go leading power factor. What doesn't like leading power factor? Generators don't like it, right? The other thing is, if I put too much capacitance, I build up the voltage. And if my voltage gets too high, now I start to have other issues, like the DC bus on the drive doesn't like that. Might trip on over voltage. So you have other issues, and you try to match this, and that's why usually they're switched in steps. Here's a multi-stage filter. So if I was going to filter more than one harmonic, I'd do the fifth and the seventh, because those are the two predominant ones. Why would I not want to put just a seventh harmonic filter on? Does anybody know? The fifth would be the worst. What happens is, you notice this is impedance, and this is harmonic order. If you put just a fifth harmonic filter on, you get that curve. If you put just a seventh on, you get that, but then this would actually go up here. The impedance at the fifth harmonic now would be worse than it was before, and you would actually have a thing called a resonant condition. You would actually amplify the fifth harmonic. So you actually have to be careful of how you apply filters, and you always want to put a filter in for the lowest harmonic order that you expect. So if you had a single phase input to a drive, likely that's going to produce some third, fifth, seventh, whatever. So where do you think the filter should be? Just below the third. Okay? If you have a fifth harmonic filter for a 6-pulse drive, that's common. The next one would be seventh. What if I have a 12-pulse drive? Where would my filter be? Just below the 11th. So I have to think about what my system looks like to decide where the filters need to be. How about phase shifting? Has anybody ever used phase shifting to cancel harmonics? You take two transformers and you put a delta delta and a delta Y, and you end up phase shifting. Yeah, it's a very good way to get rid of harmonics, because now you don't have to worry about that overcompensation with harmonic filters. And a lot of times you need transformers anyway, either to step down, or maybe you're using drive isolation transformers. So you take two currents that look like that, you combine them. This one doesn't get shifted. This one gets shifted by 30 degrees at 60 hertz, but it turns out your fifth and seventh are shifted by 180 degrees from each other, and you end up with what's called a 12-pulse system. Your fifth and seventh cancel each other from here and here. I'll show you a video of that later, but it really works well. So it's a really good way to do that. Now, what if this drive's only running at half speed and that one's running at at full speed. Now I don't cancel all the harmonics, but instead of adding, let's say this one produced, let's say I didn't do any phase shifting, 10 amps of fifth harmonic, 10 amps of fifth harmonic. I don't do any phase shifting. Up there I have 20 amps. What if this one does 5 amps and 10 amps? Now instead of being 15 amps, it's actually 10 minus 5 or 5 amps left. So I went from, I've reduced my harmonic current substantially. So any phase shifting is better than none, is the point. You can do that with individual drives. You can do it with a whole MCC. Here's a 18 pulse, or what we call CPX, or clean power drive. Okay. So again, 18 pulse, we're going to typically have 17th and 19th, and those are your predominant harmonics. And so the waveform looks very, very clean all the way up through. Where do we start talking about 18 pulse drives, or typically 150 horsepower and bigger drives? Smaller drives, it's usually more cost effective to do something else. This probably less than 50 horsepower, and somewhere in that range between 50 and 150, you start thinking about where's the cost benefit of going to an 18 pulse drive. And I mentioned earlier that our 24 pulse, our medium voltage drives are 24 pulse. So anyway, you have to think about which harmonics are going to be attenuated and reduced, and that's really a good way to do it. Here's phase shifting with 24 pulse. So I take 4 drives and I phase shift 6 pulse drives, 0, 15, minus 15, and 30, and I end up with waveforms that look like that. It's almost perfectly linear. If I have that on my system, I don't need to worry about harmonics anymore. So it goes back to what systems were designed for 35 years ago, right? They were designed for 60 hertz voltage and current, and that's what you're going to get. Very, very little harmonic current. Again, what they've done with UPSs is they've put active rectifiers in the front end. So our new 9395, 9390, 93 PM, those are active rectifier UPSs. What they do is the rectifier on the front end uses IGBTs, just like the PWM on the output for the UPS or our drives. But what happens is they took out this big transformer and they took out a big harmonic filter and they replaced the front end of the drive with this IGBTs, okay? So they took out a bunch of cost and physical size and weight and all this other stuff, and they put in an active rectifier. So from a cost standpoint, it's the same price or less to make that front end of that UPS, much better in terms of harmonic current. So this is what it used to look like, this is what it used to look like with a 6 pulse, and this is what it looks like with an active rectifier. Now, if you take that same thing and say, okay, should we do that with all our drives? Again, very high percentage of the drives are 6 pulse drives. Now, instead of taking anything out, we're just adding additional costs. So that's where, an active rectifier on a drive doesn't always make a lot of sense because you're adding, a lot of costs. It depends on the application, but going from 6 pulse to 12 pulse to 18 pulse, and then going to the next level really just depends on cost. And that's why, again, in the UPS or data center world, that's why they get away with it. This is a broadband filter. So like taking and putting essentially what a broadband filter is. Here's my harmonic source, my drive. Normally, I put this drive in, it pumps current back up through the system. What I do is I hang this filter off of here, which is a reactor and a capacitor. Okay, and the harmonic current wants to go into that. That's a standard filter, but a broadband filter also adds a big inductor here, like a 10% reactor. Okay, what that does is it forces the current to get to this point and it says, wait a minute, I don't want to go back that way. I want to go this way. So by doing that, you end up with this being a much more effective filter. But the problem is, again, you're adding this on every single drive. So you end up trying to decide whether or not that's more cost effective than doing something else with a drive, or maybe putting one filter on there for a whole bunch of drives. Active filters. So an active filter would be kind of a system level fix where you have a whole bunch of drives and you don't know what speed they're running and what kind of harmonic output they're generating. But then it'll kind of match up and inject equal and opposite harmonics. So it It sees a load that looks like this, it injects this, these two added together look like that. Does it have to be perfect? No. It just needs to be better than it was, or better than kind of the threshold of pain, so to speak. Okay? And that's actually becoming more and more common. People are using a lot more active filters just because it's something you can design up front that you don't need to know precisely the exact harmonics, whereas a harmonic filter, a lot of time you need to know a little bit closer to the actual harmonic current you expect and the power factor of the system that you expect so that you can do it right. This is just a kind of a simple cost comparison. So if I were to do nothing but put line reactors in there, I've actually done it at a pretty low cost, right? But if I don't put, if you put a drive that doesn't have AC or DC reactors in there, you know, you're going to have a lot more harmonic current, and it doesn't really cost that much to really add in that reactor into the drive and really get that benefit. So this is kind of a really key point here, is this is a very inexpensive way to get the harmonics to a reasonable level. At that point, then you deal with them another way. Active filters are probably even higher than this, but you know, $150, $200 per kVA or so, and you start to look at, well, that's a fairly expensive thing. So if I can do some of these other things to make the harmonics lower, like phase shifting, and then I kind of tweak the system with my active filter, it's a good design. It's a good way to do it.